So Seamus, you happy for me to start?
Please. Thank you, Alan.
Okay, thank you. Well, welcome to everyone on behalf of the CEA and the November Lectures in their new format. Thank you to Seamus and Madeleine for running this on chemistry and sustainable development. Now, just a bit of background on Seamus. So Dr. Seamus Delaney is a science educator, lecturer and researcher in the School of Education, Deakin University. He has worked as a classroom teacher, head of science, head of e-learning teacher, educator and researcher, both in Australia and Switzerland over the last 15 years. Seamus' research interests are chemistry education, the incorporation of augmented and virtual reality into teaching and learning, and science education in out-of-school informal learning contexts. Presently, Seamus is involved in an ongoing international interdisciplinary project with chemistry and education researchers focused on repositioning chemistry as a sustainability science, and many teaching and learning resources from this research are available on the Elements of Sustainable Chemistry website, which I'm hoping Seamus will share with us. An interdisciplinary group he co-established with Dr. Madeleine Schultz, School of Life and Environmental Sciences. So thank you, Seamus, and I'll hand over to you to introduce Madeleine.
Thanks, Helen. Well, you just did a very good job of introducing her then. Anyway, yeah, so Madeleine Schultz is here as well from the School of Life and Environmental Sciences. We're both from Deakin, and so we've really just taken this opportunity in this workshop to run through some resources or activities that we've developed probably in the last 12 to 18 months. Madeleine is here. Madeleine's going to keep an eye on the chat if you're late. So yeah, if I can be conscious, I can just throw it all out there, and sometimes I have to be stopped. So Madeleine's got two purposes. She's going to keep me to the time, but also to monitor the chat and answer your questions. So you ask away whenever you want, please, and one of us will answer as we go along. But we do have a fair bit, so we'll kick straight in. I'm just gonna, no, so okay. So start with a bit of interactivity. So if you know Menti, if you've got your phone handy, jump onto menti.com. I'll put and then there's the code there on the top of the slide. So hopefully you can see that. And it is, you can go to Menti, just put the code in, and just simply ask you, just put a couple of words that come to mind when you think of chemistry and sustainable developments. So let's see.
Seamus, you need to go back to your Menti presentation and go back a slide, because this is taking us to the second Menti question.
Oh, no, is it? All right.
So just have go onto your
I can do
Mentimeter website.
Because it's not, boom. Am I on now? You see it now?
I'm just reloading.
I'll just reset this up.
Are you sitting on a drill? Oh no, that's.
I'm not sitting on a drill.
Okay, it's all right. I muted them. It was someone else.
Now can you see the word cloud?
I'm just going to enter it again. 2, 3, 8, 4, 5, 6, 8. Nope, it goes straight to the ranking question.
Try and present that one.
Here we are. The presenter has changed slides. Now it's gone to the word cloud question. Okay, now everybody else try that.
Everybody, hopefully, sorry. Well, you've used that time to get in your Menti and you put the code in. I might do it too. See that? Oh, here we go.
Nobody's doing it.
See if I can.
Yeah, I'm going to put the link in like this.
Start countdown. Let me see that. No, it's not going to take a minute. No, a few more coming in now. Here we go. Yeah. I think you had to choose 3. We'll come back. We'll keep it for another minute. But as I said, we're going to come back to that. I'm going to show the map at the end, just to see if we've move the dial a bit on what you've seen and some of the things there, but you can see clearly, you know, energy is up there.
Now it's starting to come in.
That's interesting though. Most of the others are pretty consistent. Yeah, renewable material science. So yes, we're going to talk a lot about sort of materials basis today, society. But yeah, a lot of water. So yeah, biodegradable, biopolymers. So that's really nice there. So we'll come back to that one. Oh, you know what? It's got 12 seconds. I'll just let it run. I wonder what will happen then when the voting closes. Now, we wanted to also, we're very keen to get, there we go now. If I just go to the next slide. So in the next bit of interactivity, we wanted to quickly ask you how important it is to you as a teacher to do this in your chemistry classroom. So we sort of chose, Madeleine, can you, I need to go.
Yeah, I think you need to go back onto your Menti. Yeah, thank you. It's working.
No, they're coming through. Now that's strange. It's not updating on the slide, but I can see the numbers have changed. So here are 4 things that, you know, you might be doing in your classroom, a very broad sense. You know, preparing students for chemistry content knowledge, getting ready for exams, incorporating real world context in the chemistry classroom, some practical activities, and developing critical thinking to become science-informed citizens. So,
is this showing our results or your results?
No, they're updating.
Is it? It's not on the screen.
That's interesting. I can see that they're updating.
Ah, now it is.
Reload. That's interesting. Yeah, it's not updating.
It's a bit
here
clunky.
We go. Oh, there we go.
Yes, much better.
See, bit of technology. That's interesting. So it's a lot of people think it's extremely important to develop critical thinking. So that's good. You're in the right place. Hopefully we can cover that today. I better keep going. So hold that thought. Systems. So we're going to use systems thinking as a basis to talk about how you put chemistry and sustainable development together. Systems thinking is sort of acknowledging the fact that many of the sort of 19th and 20th century solutions that chemistry and material science has given society have somewhat led to the 21st century problems and challenges that we're facing today. So to incorporate that into our chemistry education, we have to probably do a couple of things. We start by perhaps acknowledging that recognizing the material basis of society as a core element in sustainable challenges. I'll unpack that a bit more later. If we do that though, then that might start to think about, well, you know, we change the way that we practice chemistry. Now, I'm not saying not just in education, but even just in science itself. You know, how we see chemistry and what chemical researchers and chemical engineering researchers are trying to do in terms of sustainability. But teachers have a role in that. We have to reorientate what we do in the chemistry classroom. So we raise those issues of earth and societal systems. And a way that we can do that is then to think about educating for the molecular basis of sustainability using systems thinking. And so sort of that, it comes all back around having molecular basis as sort of an approach to incorporating into our teaching. I'm going to use the other lens though for a second, material basis of society. And so one thing that we've been doing is thinking about endangered elements. Have you heard of endangered elements before? I just gotta get, no, I can't get that out. Endangered elements are all those ones there in sort of the yellow, the orange, and the deep red. The deep red ones are that we're in serious threat of running out in the next 20, 30 years. If you can see my camera, I'm not sure if you can, but I'm on campus. That's quite a rarity nowadays here at Deakin Burwood. But behind me is our massive periodic table of endangered elements, where we put a lot of those. It's not a Zoom background. A lot of people think it is, but it's there on the slide as well. Thinking about, you know, zinc. Zinc is predominantly used to coat our roofs so they don't corrode, our metal roofs so they don't corrode. Well, you know, 70 to 80% of that is used for that purpose, and zinc could run out in 20, 30 years. Germanium, gallium, arsenic, a lot of these are used in metal alloys for our tiny tiny things in our electronic devices. We can't imagine a world without these devices nowadays, and yet we might have to, because within a generation we could run out of these vital elements. So we're trying to set up a culture and conversation in the classroom, thinking about, well, students are pretty savvy at talking about, let's say, endangered species. That's quite a popular sort of activity, doing a poster around that. Why not make it about endangered elements as well? Just to drive that point further more, you know, think of the way that plastics are used all across society. They're such an essential component of everything we do, and yet nowadays, you know, so much research is going to showing the permanent chronic impacts that they're having on human health and environments. They're now in our food. They're in our drinking and water supplies. They're just the amount, but we can't get rid of them because, you know, they're in our smart technologies. They're in our energy generation. So, you know, so we've got to find a balance, and part of that is helping students to reason so they can take affirmative action on these challenges. Traditionally, we might say that in chemistry teaching, we focus on the parts. You know, we take very much a bottom-up approach. We love to categorize things. We've all been there where we've sort of had solids, liquids, and gases, and we talk about their properties, or we talk about covalent, ionic, metallic bonding. You know, we've got that emphasis on categorizing and talking about the properties of something. But that sort of divorces a lot of that from actually what we're interested to look at, because we're learning things in isolation. We're taking perhaps a stepwise approach of approaching the issue. It helps us as a teacher. As teachers, we can sort of look at how we can analyze and diagnose what a student is learning. Students ask us questions, and we go, oh, well, you know, I can see where you're going with that. And so it feels much more active. So as I said, we're not saying this is a bad thing. You know, chemists need to be analytical. You know, they need to be able to explore matter and, you know, analyze it and elaborate on its properties. But it's not enough. That's what we're really trying to throw in here. Now, I'm going to try one more Menti. Madeleine, tell me if this works. We thought we'd ask one more question on Menti before we drop Menti.
Yep, it's working.
Perfect. How do you use this equation in your teaching? So the one at the top, ammonia plus 3 hydrogens goes to two ammonias. The Haber-Bosch process. You know, Madeleine and I put our heads together and we chose a few of these. Obviously, we could have put a lot more, but we'd be here all day counting. So yeah, scores are coming in. So look, preaching to converted, we're all chemists. So yeah, understandably, equilibrium and balancing chemical equations are quite high. So yeah, that's
you need to refresh, Seamus. We can't see the results.
Oh my God. I decided I don't like Menti. Can you see it now?
Yes.
Wow. So see, look at that. So balancing equations, equilibriums, bonding, that's quite high. Chemical warfare, a bit on the bottom side of things. Again, maybe because we're thinking about, we want to talk to the equation, not necessarily its utilization and its intended and unintended consequences. But fertilizers is high. So we're having the right conversations. I guess now it's probably thinking back, can we pitch that in a different way? Great, thank you for everybody for doing that one. So let's embrace the complexity. Let's not pretend chemistry is simple. Let's just embrace it. We're talking about wicked problems. We're talking about complex problems. We need to jump in and deal with this. We have to incorporate contexts. Real world contexts. We need to start being thinkers and design thinkers so we can start to innovate in chemistry and chemistry education. We have to still have all of our mechanistic and our student reasoning and our, as I said, our analytical approaches. That's not going out. But we can start thinking about taking action in sustainability. So one way might be, for instance, circular economy instead of linear economy. Just going to do the old mute all again. So that's where the molecular basis of sustainability comes in. Madeleine, do you want to mute all everyone again? Is that something I can do?
Sorry, what do I need to do?
Can you mute it all again? It's just sort of,
I think everybody's muted.
no, that's strange. Someone's keeps coming up. So
Maybe it's you.
maybe it's me. It probably is. So here's the two then. So sorry, that's a very busy slide, but just to talk to you just quickly, the one on the left is that sort of traditional teaching. The one on the right then is the systems and the holistic thinking. So context driven, focusing on the whole, focusing on relationships between things. So, and helping students to see the overall picture before they try and solve a problem. They might, as a teacher, you might pose the question, but then students need more time to develop and solve a problem. Unfortunately, as a teacher, it's difficult to see. Students appear to be much more passive in their learning because they need more time. They need time to put things together before they know what to ask a teacher. So it's frustrating in that sense that maybe we can't diagnose system thinking as quick as we can in traditional teaching, but that's a trade-off here where we have to think about. So we're going to play with that space. We're going to play with transformation, synthesis, analysis, matter. That is what we do in chemistry, right? We do have systems though, and I'm not talking about just simple biological systems and carbon cycles, though that's important as well. Not necessarily about Earth systems and sustainability policy, but we can play a bit of that space in the middle. After all, it is the chemical basis for those systems that I just said. So we can talk to that in a sustainable class. And it is in the curriculum. I'm sure you're all fantastic teachers, so you make sure you incorporate the cross-curriculum priorities into your classroom. But if you've gone in, if you've dug into the sustainability, how it's described in the Victorian curriculum, you end up at these 3 dot points: systems, worldviews, and futures. And if you look into the wording there, the language is there. System thinking is not outside of the curriculum. In fact, it's there. It's been there all along. It's just perhaps we need to be a little more explicit in our approaches. So that's what we're going to do now. We're going to, for the rest of today, that was the intro, by the way. For the rest of today, we've got slides here on a few different things that we've done in the last probably 18 months now, Madeleine, and also some things that we're doing in the future. So, if you're watching this video afterwards, you can pause and stop and take some of the resources to do with us today. We have a couple of things for you to do along the way. And so hopefully you can join in. But let's start with the first one. So practical activities. Yes, we have designed a whole heap of practical activities that we designed for an outreach program. We received some money from the Australian National Commission for UNESCO. And as part of the International Year of the Periodic Table, we went out and visited lots of schools around rural and regional Victoria. Worked with P12s, primary, secondary, and we took student leaders. We had some university volunteers with us. They were fantastic help, and I'm really appreciative of all the work they put in. But also we had student leaders at the school. So these were generally senior students, year 11s, year 12s, who were helping out run the activities. And so here's some of the practical activities we did. We made a metal air battery, an aluminium air battery. Now we're going to do that one in a second, so I might not talk to that one right now. We grew copper crystals on an aluminium sheet. We dunked aluminium into some copper agar gel, and sort of the copper crystals grew. All of these resources, the student resources, the teacher resources, are up on our website, eschemistry.org. We burnt 1 cent copper coins at risk of being thrown in jail by the Queen. We took, I bought 1,000 1 cent coins, not for $10, a bit more than that. And we coated them with a zinc, and then we stuck it in a blowtorch to get them gold. So we had bronze, silver, and gold 1 cent coins. Again, that was an analogy thinking about zinc plating and the use of zinc and metal surfaces. We did writing with iodine and fingerprinting. That was just a story about the elements. We wanted to have all of these. There's a couple more. We had a box of 33 elements in a little, food container, and we printed out these A3 sheets of that table, the periodic table of endangered elements, and had them move them around and put them on there. Here's a group of boys and girls having a bit of a competition to see who could do it first. We bought some gallium and having the students sort of handle a metal gallium, and at the same time we could have a talk about what gallium is used for. Professor Stuart Batten, who designed those element sets, was very nice and gracious, and he gave us his periodic table briefcase, as you can see there in the picture on the right. And we had students sort of handle so many of those elements. Because what we were trying to do with these activities, not just the sets, but also the other activities, is have stories around elements. So many of those sort of classic chemistry practical activities, or even outreach activities like, your elephant's toothpaste and things like that, they're very complex stories where the chemistry can't be easily talked to. We designed these ones where you could talk about what the element is and the chemical properties of the element, and having that connect to the story about what the element's used for. So again, bringing back that idea about materials basis society. We did have to have an explosion, so we always ended up with our mini thermite reaction, just a teaspoon of aluminium powder and iron oxide for a little explosion of thermite. Now, that wasn't our practice. We didn't come up with that one, but we found one in the Royal Society of Chemistry, and we put the details up on our website. Very safe to do. Don't do it in a fume hood. Just do it out on the bench. Big box of sand and water, catching it all underneath. And yeah, just light it with a sparkler, a little birthday sparkler. It brings up a story about, why aluminium, after all, aluminium is such a core component of our society, without really realizing it's 3% of all of the globe's electrical energy supply is used just to make aluminium. It's worse in Victoria. About 10% of all of the electricity generated in Victoria is used in one place, a smelter out in Portland in Western Victoria, and just to extract aluminium from aluminium ore. And yeah, it could be done so much better. Recycling aluminium takes approximately 5% of the energy requirements to make it from aluminium ore. So that's the conversation that you have with students. Because after all, why do the thermite? Well, that just so fantastically shows that aluminium, as a group 3 metal, it takes, when you release the energy from aluminium, a lot of energy goes into making aluminium, so you can get a lot of energy out of it. So it's time. We are going to try something a bit risky. I hope you've got a few things there. We sent a materials list a couple of days ago to make a metal air battery. So this is where I'm gonna talk to it. I'm gonna just set up my camera and have it here, and I'm just gonna make one, and you can follow along. We do have all of the teacher and student resources, including the method, up on our website. We had some second and third year students work with us this year, and so we never met them. It was COVID, but they did some great things online for us, and they made a video, including a video that they've made showing you how to make a metal air battery as well. But I'm going to try and do it right now. So,
Seamus, can I suggest that you stop the screen share so
yeah,
that
that's what I'm doing right now.
Yep.
Because I'm trying to get out of.
Make yourself big.
Make myself big. Yeah. Let's
just go stop share.
Stop share.
There we go.
It's going to get my stuff. Hopefully you've got it too.
So if you want, if you don't know how to do it, on the top right-hand corner in Zoom, there's a view option, and there's gallery view. Everyone will be little, but if you go speaker view, you'll get a big Seamus and little everyone else, and then you'll be able to see. And we hope that some of you will also have a go. This is the most fail-safe, robust, easy, cheap, and fantastic demonstration of the electrochemical potential of aluminium.
So let's give this a go. Huh? So now it's just so super simple. It's almost kitchen chemistry. You'll see why in a second. It's not quite kitchen chemistry, but it's very close. We've got. Am I coming up on the big screen?
Yep, perfect.
I can only see your face, Madeleine. It's quite frustrating. I can't see what I'm doing, but anyway, I can see in front of me using my own eyes. I've got a piece of aluminium, so I just cut it, to 5 by 5. All you need is a bit of paper towel. On the days we did filter paper, but we went through so much filter paper, we quickly just figured out we just use paper towel. And I have some salt water. Madeleine assures me you could easily just do this with water, but just throw a bit of table salt in there, use tongs, which I don't have, and then just lay it on the top of our aluminium there. Now, I need a little bit of charcoal. Again, works without it, but you want to make the emphasis that it gives a sort of a surface for it to happen. So I've got a little bit of charcoal here. You don't need much. When we did this in schools, students would lather it on, but just the smallest amount will do.
So this is actually a really interesting question, like a thinking question for the students. Does more charcoal give more voltage? And obviously no, because charcoal is just a current collector, or you can think of it as a catalyst for the oxidation reaction to take place, for the reduction reaction to take place. But it's a good way to get students to think about what the purpose of each component of a battery is. So not everything in the battery is actually taking part. And in this case, it's a form of fuel cell because its oxygen's being reduced and aluminium's being oxidized. And the salt water is just the electrolyte. The paper towel is just to hold it all in place. And the charcoal is the current collector.
So I've got a bit of wire. It's got a bit rough, tough, but it's just simple. Yeah, Kai, you asked during the day. It's just simple wire. We bought about a big roll of 25 meters for $5, and we still have 24.5 meters of it left. You just cut off a little bit on either ends. So just take a little bit of the sheath off so you get a nice contact with the metal, and just plonk it in. Just plonk it in, and then what's now been known as the burrito style, just sort of roll it up. So you've got, and just press it down so there's nice contact there. And now we've got our two contacts. So I want to attach one. I've got a multimeter. I'm going to turn the multimeter on. So I feel like a magician just to prove you. See, look, it's on 0. And then I'm going to hook it up to. So one side, we're going to hook to the wire, so the exposed wire that's sticking out. So you can see that that's sort of you've got the wire hanging out there. And the other, if you're following along at home, to the outside of the aluminium foil. And oh no, I've got it around the wrong way. Just flipperoo. Lo and behold, you see that there? Yeah, about 0.7. That's not a bad one, Madeleine. So yeah, about 0.7 is about as good as we get at these. But if you think about that's 0.7 volts out of a piece of aluminium foil and air. Yeah, that's it. So you can talk to this. The narrative here would be thinking about metal air batteries. So there's a lot of research going into zinc air batteries, aluminium air batteries, magnesium air batteries for stationary intermittent power storage. It's a huge project here. Here at Deakin University, we have the Institute for Frontier Materials who are investigating this right now. You can't. I couldn't find my my LEDs, Madeleine. But we try. If that's not enough, if the students that sort of don't feel like they've got enough of a result from that, what we did do is you could get about. We had a student, Stefan, who figured out that we put about 3 of these in a row. So again, when we're doing this in outreach, and if you did this with your class, you could have a whole heap of them doing together. It takes about 3 or 4 of these in a row. And you can get to about 2 or 3 volts, and that's enough to light a simple LED. So if students, if they want a visual, if a number on a multimeter is not quite enough of a visual for them to buy into it, they can about 3, maximum 4 of these in a row. You'll light an LED pretty easily. So there you go. Is anyone having a go? Did our attempts to have a bit of a Zoom? If I put back the gallery view, I welcome you. If you have had a go, I welcome you now to turn your cameras on and show it to all of us. I wonder if I can get the gallery view going again. See if anyone's brave enough to show it on the screen. Not yet.
Yes.
Oh, there we go.
Guys, go on. Fantastic. Did it work?
That's an impressive multimeter. Yeah, good. You've got it hooked on the outside.
Helen's got it going. Well done.
Yeah, Em's done it. Bravo.
Oh, Lisa.
What? Done.
I'm so impressed that you guys doing your. Oh, someone else did it. Oh, well done. In a lab with lab coats and everything.
It's going to take. No, that's really good. Oh, I missed the photo.
Fantastic.
I'll take a photo later because hopefully it's all been. Oh, it's not recording, is it? Oh, it should be recording. There you go. Yeah, look, there you go. So that was it, really. It's super simple. I guess the only thing would be probably the wires from the battery, but this could easily be done as a kitchen chem track. But you know, I'm sure not many kids have multimeters at home. But yeah, there you go, Helen, 0.69. I've never seen anyone get above 0.77. That's the highest I've seen, but I think the kid was probably cheating. There we go. Should we keep going?
Yes,
yeah,
press
feel free
on.
to keep asking. If there's any other questions about that along the way, don't hesitate to ask us. You could turn in a bit of investigation to like what makes it, you know, which parts are necessary, as Madeleine pointed out, you know, taking the carbon away, even not just using plain water. There's all sort of ways of thinking about, you know, measuring the different voltage and so on. Okay. Let's keep going. Oh no, I got to share screen again. Voila. Okay, moving on. The next couple of activities incorporated the United Nations Global Goals for Sustainable Development, which I should probably just quickly introduce. They are 17 goals that have been set by the United Nations, and they are transformative goals that the world has set themselves by 2030. Now, that means that this has become somewhat of a framework to evaluate society's, you know, improvements and movements towards where we want to be. So it becomes a way of evaluating scientific, ethical, social, environmental issues, not just in society or in media or in the public space, but also in the classroom. And while some of them don't scream out as chemistry, some of them certainly do, but you could definitely talk to the chemistry of all these. And so that's what we're going to do now. Just a couple of ways we've been doing it is with systems maps. I'm sure many of you have, oh, thank you, Madeleine, for the acknowledgement where the battery came from. I'm sure some of you have done mind maps and concept maps with your students in the classroom, not just in chemistry, but also in lower secondary. So a systems map is just taking that a little bit further. We put a chemical process in the middle, and so in this case, it's our favorite again, ammonia. And then you put all the ins and outs. And so start to think about all the ways that, you know, all the things that a student know about that chemical process. Now, we don't stop there though. What we go is then we say, no, a central learning outcome for chemistry is that chemicals and chemical processes have benefits and hazards. After all, this is a complex. We're embracing the complexity. And so we really need to consider these benefits and hazards together. You know, the negative and the positives help us really much more build an overall picture. Think back to systems thinking, an overall picture of things. And so we do that by, this was an example where we had that. Students had to first be introduced to the Sustainable Development Goals a little, and then they had to label all the things in their map to a Sustainable Development Goal. And then make a judgment. Do they think that's a positive thing or a negative thing? And so you can have some obvious negatives there. You're thinking, I'm sure they could have thought of one positive, but they were gone with 3 negatives for explosives. So that overall, they've put that as a negative aspect. Plastics, however, they can see many positives, but also some negatives. But overall, this student has thought that that's sort of a largely a neutral thing. So it becomes a fantastic way to really start to evaluate the impacts be it positive or negative, of a chemical process in the context of the Sustainable Development Goals. So we won't do one today. As I said, we've got one more interactivity, but it's not this. This is what we've been doing. I've done this with pre-service teachers this year. We've done it on workshops at the STAV, the CEA last year. We ran workshops with Deakin, secondary and tertiary educators and researchers, and we just made them make these maps and you know, put a process in the middle. You know, here's a few: addition, polymerization, formation of sodium hydroxide and chlorine gas, contact process, water filtration, ocean acidification. We even had some of the teachers that we've been working in the CEA Professional Learning Communities project. Ollie, I think, Ollie, if you're here, you had N95 masks. This was back in March and April, before those things were, when the price spiked, and talking about why they're so important and all the materials that go into making N95 masks. So there were so many fantastic ways that they could talk to. So that sort of list there is a way that you could do this in your own classroom as a way of incorporating it and then making a call overall. So just an example, as I said, you know, with polylactic acids, we did this one on Padlets. This is one with a student, it's an actual student, and so they've gone off and labeled things and color-coded it with polylactic acid again. This one's a little more complicated. This is the one looking at ocean acidification and really starting to dive deep into the role of anthropogenic emissions and how that is changing our life and aquatic system. So really nice way to connect to that story. But do you feel like you could do it? So we've got a Google Doc there. Now I need to, here again, I need to come out, I need to share, I'm going to share the link and I'll put it, just copy it. I'm going to copy and stick it. Oh, see, here's one that I prepared earlier. I'm going to stick it in the message chat. And so you can go to that Google Doc. Now I'm going to bring it up on my screen as well. And we've made a simple Google Doc. Go away.
Have you ever used a computer before, Seamus?
I feel, you know what? I was so much better when I just did everything in my bedroom with one laptop, and that was it. Now I'm in a room that's got 3 screens. It's I'm getting technology overload. So let's get rid of that one here. So this is our Google Doc. So that's fantastic. I can see you're in it. So I'm not the only class. And I want to share my screen again. Here we go. Now, so this is our Google Doc. So I was really inspired. One part of COVID has been able to go to so many other things this year international. I was very lucky to go to the Green GCE, the Green Chemistry and Engineering Conference in June. It was in America, but obviously it was online. And I heard from Tamara Freeman, who had this fantastic quote. I love it. Sustainable society requires that we make all the molecules we will ever need only from the molecules we will always have. And so I think that's a nice way of encapsulating this. So what I want you to do now, and we're going to throw you into breakout rooms. We're going to give you 10 to 12 minutes. I know that's going to push us up to the limit, but I can wrap up pretty quickly with the rest of it. We want you to, you're all going to work in the same Google Doc. You're not going to go off to different documents. But if I scroll down, what we made is just 2 columns, a simple, you know, how can chemistry help society achieve the Sustainable Development Goal? And so they are some there in the first column. And then we thought, well, have you thought about this? You know, have you thought about a teaching learning activity you currently do, or one that you'd like to do, but you haven't really thought it through entirely, and you might just jot down some ideas. Those links there will send you off to get a bit more information. But I think you can probably see, yeah, some people are jumping into it. Those numbers and names are pretty self-explanatory. So let's go with the breakout rooms. We're going to make about 8 rooms. There you go. It's about 4 to 5 people per room. We'll come back.
Yeah, just when you go into a breakout room, you will suddenly find yourself with a bunch of strangers. And I know everyone's got cameras and mics off in the big room, but it's really nice if you can put your camera and mic on if you possibly can, or at least your microphone in the breakout room, and have a chat, get to know each other. There's people here who are working as teachers. There's people here who are working at other universities. I think there's some other people here. I don't recognize all the names. So you don't have to get straight to work. Have a little chat, get to know each other, and maybe chat, because what I can see already on the document is that people have lots of ideas of how chemistry can help, but not very many ideas of TNL activities related to these SDGs.
So let's get into it then. I'm going to send through, we'll bring you back in about 10 minutes, okay? Go for it. And we'll flow. Okay. Right, and we're going to throw them in again. I'll just send that to everybody in case I've got it. Oh, you're in a room. There we go. Yes, not enough time, Nick. We could have easily done that one for a lot longer. We will keep that document live. I really encourage you to go have a look at it, you know, steal ideas from it. When I saw Tamara do that, she actually would run that with her first year chemistry classroom. It was day one, class one, with her first year chemistry students. And they would be given this task. You know, pick an SDG and write things to it. And she would just keep the document up for like a month. And it became a way that the students had to talk to that and refer to it. She didn't have the second column. Obviously, the second column was just for us teachers and teacher educators. She just had the first column. But that could be also an activity you could do with your students. Wouldn't that be amazing if they walked in on year 11 or year 12 or even year 7? You know, they were in class and they had to suddenly start thinking about, no, chemistry does actually address these sustainability challenges. They won't immediately come up with the answers. After all, there aren't answers. There's only problems. So it could be a fantastic way to challenge students to come up with it. If there were answers, this was a paper from the, oh, and now I have no idea how that's on the screen now. Here's a few that were in a paper. I'll put all the links in the bottom there. You know, you probably had some of these. I love the female statues, female chemist statues. That's a winner. That someone had that one. But just some of the other ones, you know, yes, we can probably easily talk to the climate change ones and such. But the ones around marine chemistry, you know, partnerships, corporations, the OECD, the OPCW, which is the Chemical Organization of Chemical Prohibition of Chemical Warfare. So there's a really nice partnership you could talk to there. In the wrap up, so a couple of things. I'm going to go about 5 minutes at a time. Hopefully that's not going to bother too many people. We had infographics. So are you bored of doing your scientific poster? You know, there's other things you can do there. We did this for the pre-service teachers here at Deakin. They were each given, so they had to go find something about contemporary chemical science practice and then make an infographic that they could use in their teaching for it. And so this was flipping, you know, chemical photo switches, ionic liquids, wearable batteries. And so these are all actual work that our student teachers did. You could easily do that with your students as well, if you want a bit of an update to your posters. Another area, as you saw, all the activities that we showed you before were very much on the lines of sort of short activities, 10, 15 minutes. After all, they were really to be used on our outreach. So we're now starting to design longer group-based, class-based design thinking projects where the teacher might ask the question, but the students then have license and to basically develop the problem themselves and innovate. Very briefly, here's a couple of sources that you could go look at one. So Two websites I've become aware of this year, Beyond Benign and the NSF Centre for Sustainable Polymers. So the links are there, and again, we'll send all these out in the follow-up. Beyond Benign is a US-based resource, but they put all of their documents up as open source Creative Commons. They're all sorted by topic. They're all sorted into high school, primary, so it's K-12. They used to also have some higher education ones. All the stuff is up there as Word documents. So they're really wanting you to take them and modify them and use them for your own purposes. A couple of ones that I've really fell in love with, I haven't actually had a chance to do them yet, but ones that I've sort of fallen in love with is making mushroom-based packaging materials. If someone throw in the chat if you've done this, but I found an Australian place that probably sell them here. I think they're out of Swinburne. You can just grow packaging, and then compare it to polystyrene, compare the strength. This would be a fantastic practical activity for a class. Recycling polylactic acid, just simply making it and then just simply dissolving it in sodium hydroxide and showing how simple it is to really degrade and break down some of these really simple biopolymers. Antimicrobials, if you can find sharklets here in Australia, but there's some really nice, fantastic material science services that are coming through. Those service chemistries, unfortunately, not as much of in our course. The other one, very briefly, is a little more higher end. It's probably more senior secondary. Some of the ones in that Beyond Benign you'll find that are really great for lower secondary. These ones are probably at upper, at least. But they're fully worked up. They've got all the details there on their website. They've got 3 fantastic activities there that you can certainly do over a longer time. The first one is making some simple biocopolymers. So using, I think, you see the winning combination, if I remember, is starch and citric acid and glycerol. And then they make that, and then they add a dye, they add a yellow dye, and then they deliberately degrade them. So it's showing that idea around, breaking down biopolymers, and they actually measure the release of dye from using colorimetry. So it's a fantastic idea to sort of talk about chemical leaching, talking about breakdown. It's got some analytical there. See, we're not throwing out the traditional approaches. They can do a graph, they can do a colorimetry. It's all there as part of the prac. Sutures, medical stitches. So you making some simple biopolymer stitches that can be broken down. Again, testing them. Again, having a good design thinking process of actually having to test these things out. So they're all on their website. We are also getting into the game. We are starting to make some of our own longer pracs. They're all there on the slide. I won't talk to them all, but how about some dye-sensitized solar cells, using different dyes, maybe even local indigenous berries to make to try them out and see how the solar cells work. Making biopolymers from crustacean waste, lobster shells. We had some third years make us that prac this year. Ionic liquids. Madeleine, if you catch Madeleine in a moment, she'll talk to you about concrete and cement for a good 15, 20 minutes. It's a fantastic story that I think we could really start to have a good sustainable chemistry conversation around. And we're currently designing those activities. But just leave you with this thought. Did you know that Australia sells sand to Saudi Arabia? So the one place in the world you wouldn't think would need sand, we're selling it to them because you need, after all, a particular type of sand for concrete and cement. So looking at ways of possibly recycling and repurposing other materials instead of using scarce resources such as sand. Microalgae for fuels, water filtration, smart gardens, the list goes on. And we're really happy to say that we've just received some government funding to continue this fantastic research. So working with Macquarie University and about 5 other universities, we've got money from the Commonwealth governments to basically run maker projects, STEM maker projects, predominantly with low SES schools, so that hence the name, but we'll work with any school really. And so in a COVID normal circumstances in 2021 or even 2022, we could work with you to either one of those problem-based learning activities you've just seen, or we could help you design another one. And we're going to run those out. We're piloting the pracs right now. We're going to run those out in 2021. So we're just email us, throw us a chat. We'll put things up on the website as they come in, but get ahead of the curve and get involved. That's not going to load, so I'm just going to skip that. So that was it. Thank you so much. Sorry, thanks for hanging around. We've got a few minutes over. We really should, as I said for the last time, there's the link to the website that we're putting up the resources. Really want to thank some of the really amazing eminent researchers in this field, Peter Mahaffey, Tom Home, Mary Kate Orgel, that we've been very lucky to be able to talk to and chat about what we're doing. There's a list of some funding that we've received so far, and we're very thankful for that. And of course, some pictures of our amazing university volunteers who went out, often sitting in the back of the ute for 3-4 hours, driving out into northern or western Victoria, and staying with us for 2-3 days doing these school outreach activities. And they were back in the lab and testing out and setting it all up. So that was really amazing. So and they will continue to have evolved when we start coming out to schools again post-COVID.
What's that bizarre scribble on your screen, Seamus?
I couldn't turn it off. Someone has managed to write on the screen. I'm just going to leave it there.
If you go up into, if you go into the annotate, you should be able to clear. Oh, it's not, yeah. There, see,
someone did it themselves. There you go. So thank you so much. Thank you to Madeleine. I have been following the chat. I managed to get that up on the third screen and see some of the things coming in. You don't need to sign up, Lee. You can get the activities. I've downloaded them. They just download as PDFs.
From the NSF?
Yeah.
If you've got a link that's not working, just paste it in the chat and we can investigate.
Yes. But thank you. We will make sure we put all the links that we've mentioned in the slides. I'll put them in our Word doc and we'll send them out in our follow-up email. I'll give it to Mick and Mick will send it out when he sends the link to the video. Okay, lots of thanks. Any other quick questions? I'm just scrolling up to see if there's any more questions. Yes, I agree, Em. We could have done that brainstorming for a lot longer. So that's why we're going to leave that Google Doc up, and you could, steal ideas, annotate that, add things to it. We'll keep that up. We are going to StavCon in a couple of weeks, and we'll run a separate one there. We might pull the two of them together, and we'll get Mick Moylan to put it up on the CEA website as well. Because I think that's the SDGs. You don't have to make about the SDGs, but the SDGs do provide a really nice framework to think about that. Like, think of the ways that we incorporated the SDGs into those systems maps, for instance. Just that simple way of taking a concept map and making it about sustainable development and making it about chemistry. So, yeah. Okay, thank you again. I'm going to stop sharing. I hope for the best. Next week, we're still going with this, right? We've still got sustainable development as a core theme with Saro, Zoe Lowe, and I hope to see many of you there next week as well. All right, thanks everyone.
Thanks very much, Seamus. Thanks, Madeleine.
Thanks, Madeleine.